This lecture is about state space models. In this lecture, we will introduce the state space representation of a model. This is one way of expressing the structure of a realization that you have observed, and it's also possible to transform the state space representation into other forms that we're more familiar with, such as an ARMA form. I'm back again. The state space representation depends on the notion of an internal state, x of t here. That is the internal representation of the model, containing structures that may or may not be visible from the observations, but that dictates the behavior of the process. Y of t is the thing we are measuring. A of t represents how the earlier states are transformed into the new states as one time sample is passed. So x of t here is a Markov process, so it has no memory. It only relies on the previous state of the process. I allow for an input, u of t. The output is seen to be represented as a scaled version of the states, and I have two forms of noises that I need to deal with. First of all, there is a measurement noise. This is basically saying that if I say, for instance, I have a thermometer, I have a problem reading the details of it clearly, so there will be some form of deviations from the true value. That is my measurement noise, W of t. That is quite different from E of t, which is a model noise. That is to say that the temperature, say, can be modeled as an ARMA 2-3 or something by approximating some form of differential equation, but it is a rather crude model. And this crudeness is reflected in that there will be an error in the model. That error sits in E of t. So these two kinds of errors are quite different from each other. E of t is a representation of the fact that my model is not perfect, whereas W of t is a representation of the fact that I'm measuring something. Anytime I'm measuring something, there will be noise. We will here assume that these two noises are uncorrelated with each other, with covariance matrices Re and Rw. We will also assume that the system as such is stable, meaning that the determinant here will have all its solution inside the unit circle. We will allow the system matrices to vary with time, but if they do not, then of course we will just drop the t as seems suitable. For simplicity, we will restrict our attention here to the real valued case, but of course you can have exactly the same kind of representation and discussion for complex value data. But to simplify things, we'll stay with real value data for now. So let's look at an example. Say that I have an ARMA PQ process that I wish to represent on state space form. To do so, let me first introduce D, which is the maximum of P and Q plus 1. And then I can just form what's called the controllable canonical form, like this. So I have my A coefficient sitting here and my MA coefficient sitting down here. I can also have an observable canonical form, then my A coefficient sits here and my C coefficient sits here. I can also form infinitely many other forms of representation by just scaling the A matrices by some transformation matrix T. There is not one state space representation for a process. Rather, there is a set of them and you can choose the ones that seem suitable to you. In particular, you would want the states to be balanced. Say that you have one state that measures something in thousands of kilometers and something else that measures something in nanometers. It is quite likely that you will get into numerical trouble because of the scale of the different parameters here. You want to choose your states such that the states will then internally have similar representation in scale, such that you do not run into numerical problems. So selecting the states can dictate how easy it is to form your solution and also how fast things are converging. Important to note here is that we are assuming that the A's and the C's are known. So we are building the state space representation out of known A's and C's, meaning that I can represent the realization of the output Y of t given these known parameters. But I'm not actually estimating these parameters. And as you know, we are quite often interested in estimating the unknown parameters, but then I have to form my state space representation in another way. Here is such an example. So here is an AR1, so I have a process like this. I will then select my state x of t as A1, the unknown and desired parameter that I seek to estimate. I will want to estimate the states x of t here, and that will then give me an estimate of A1. If I do that, the C matrix will be this. This should of course be a Y, such that my state matrices A, B, and C are formed like this. So if I were able to estimate the state x of t, I would then automatically get an estimate of A1. So typically we don't know the value of A1, so we will set an initial value to be 0, which being our best guess of it. Say that the true value was 0.6. If I were to estimate the state x of t, I will typically get then some form of convergence starting at 0 and then going up and moving around and converging slowly to the desired value like this. We term this the overshoot. And depending on what kind of processes your model, that might be desirable to limit this overshoot so that it cannot take too large values. Say as an example that you're controlling a nuclear power plant. You really do not want it to have large overshoots here. You want it to be very smoothly and stably ending up at the desired location. The smoothness of this curve depends on the assumed covariance matrix of the noise. The more interesting part is when we allow A1 to change. We're basically saying that we don't know A1, but we also don't know if it's a stable value of A1. So say, for instance, that the seasons are changing over the year and you try to estimate the outside temperature. Obviously, this parameter is not going to be stable, so it will change over time. How can I do that? The way you do that is that you add a model noise like this. You're basically saying that the state that represents the value of A1 is imperfect. effect. So there is an error in your model, and this allows the value to change. The level of the covariance matrix Re here will then dictate how fast you are able to adapt to those such changes. So here would be an example of a change. If I have a large Re, I will react very quickly, but I will also have a problem to converge, something like this. Whereas if I select Re small, I will on the other hand have a long time to converge, but I will converge smoother, but I will adapt slower to changes like this. So by selecting Re and Rv here, I am able to decide how fast should I change, how conservative should I be, and how much variability can I expect in the end results, and how fast do I want things to converge. By controlling these two matrices, you have the way of controlling the convergence of your system. Here is another example. This is of the Swedish fighter jet Gripen, and this is the actual state space representation of that fighter jet. So this is just to show you that you can have very complicated systems that you dictate by a few states. Finally, I would just make a note that we can transform the state space representation back into transfer function form by just using the Z transform. I'm just noting that this is the same thing as x of t plus 1, allowing me to rewrite it like this. Multiplying by the inverse will give me this, and therefore I have the two transfer functions between the input and of the noise process like this. If I express those, I will then get back into this transfer function form that I can represent as an ARMA. The book will have more details on this.